To learn how to use ultrasound effectively, it is useful to understand the basic physics and its clinical concepts. Ultrasound imaging systems use a transducer, also called an ultrasound probe, to send sound waves into the patient's body. These sound waves bounce off different tissues within the body and return to the transducer. The returned sound waves, or echoes, are processed by an ultrasound engine to produce a black and white image of the organs. Ultrasound is a series of tiny mechanical pressure waves propagating through the body. These sound waves are generated, transmitted, and received by an ultrasound transducer. Now, let's see how this works. The ultrasound transducer contains several piezoelectric elements that are excited by an electric current. An electric current applied to a piezoelectric element causes the element to expand and contract, creating a pressure wave. These pressure waves propagate through the tissue in the body. The echoes reflected from the tissue return to the transducer elements and are processed to create ultrasound images. An ultrasound image is a cross-section inside the patient that is formed line by line in front of the transducer. Here, we see how a typical image of the right kidney would appear on screen as the user positions the transducer at different angles. To produce images, an electric current is applied to the elements in the transducer. This generates a transmitted pulse or a sound wave propagating through the patient. The sound travels rapidly through human tissue at approximately 1,540 meters per second. As the sound wave reaches internal structures, reflected waves are sent back to the transducer surface. The waves are processed to generate black and white images. Since sound travels back and forth at a known speed, the system is able to interpret the signal and display structures at their exact location on the screen. Shallow structures, which reflect first, will be displayed at the top of the image. Echoes from deeper structures take longer to return and are displayed at the bottom of the image. This processing is done rapidly enough to display moving images in real time. Understanding sound beam interactions, including attenuation, reflection, and the effects of frequency. With ultrasound, the major source of sound wave attenuation in soft tissue is absorption, which is the conversion of acoustic energy into heat. This results in the ultrasound wave becoming weaker over distance. Deeper structures can be more difficult to see with ultrasound as the signal attenuates. Most ultrasound systems compensate for weaker, deep signals by increasing the time gain compensation, otherwise known as TGC or gain, at deeper levels. Increasing the TGC or gain brightens deeper structures to improve visibility. Reflection occurs when a sound wave encounters a boundary between two different media, such as between tissue and bone. Some of the wave bounces back toward the source of the echo. The reflected angle of incidence is identical to the transmitted angle of incidence. Structures such as bone are strong reflectors, which means that most of the incoming wave is reflected by the structure. In this case, an acoustic shadow will be created. Scatter occurs when ultrasound waves encounter a medium with a non-homogeneous surface. A portion of the sound wave is scattered in random directions. The consequence of scatter is known as speckle, which produces the grainy appearance in an ultrasound image. For sound to travel through the body, the medium must be acoustically coupled. Since ultrasound is reflected by air, we need to use gel, and there has to be proper contact between the transducer and the patient. When air is trapped between the transducer face and the skin, it reflects sound waves and creates shadowing. A good example to demonstrate the concept of sound frequencies is listening to loud music played in the home next door. The bass, or low frequency, is often heard through the wall. Higher frequencies are often attenuated or absorbed by the walls of the home. One cycle of a sound wave is composed of a complete positive and negative pressure change. The distance traveled during one cycle is called the wavelength. The frequency of the wave is measured in cycles per second, or hertz. Audible ranges of wavelengths heard by humans are between 16 and 20,000 hertz. Ranges higher than 20 kilohertz are not heard by humans and are considered ultrasound. In the case of typical ultrasound imaging, the frequency range is between 1 and 20 megahertz. Smaller piezoelectric elements vibrating relatively faster generates higher frequencies. Larger piezoelectric elements vibrating relatively slower will create lower frequencies. Several parameters affect the clarity of an ultrasound image. One of them is frequency. Lower frequencies are less attenuated and provide better penetration, which is good for deeper structures. Higher frequencies provide better resolution for shallow structures. For optimal imaging, it's critical to select the transducer with the right frequency for the anatomy being examined. Let's review some highlights about the physics of ultrasound. Ultrasound images are formed by listening to echoes from structures reflecting a generated ultrasound beam or sound wave. As sound gets attenuated while going through tissue, the signal gets weaker in deeper structures. Ultrasound systems amplify these weaker signals to brighten the image for better visibility. Higher frequencies provide higher resolution images for shallow anatomy. Lower frequencies enable imaging deeper inside the patient. Absorption may prevent imaging behind solid structures. Reflection may prevent imaging behind solid structures or air.